Hi guys, welcome to a lesson of partial differential equations. So now we are going to start the topic of Laplace equation. In the previous lessons, we talk about the wave equation, we talk about homogeneous, non-homogeneous wave equation, and with some various type of boundary conditions, time dependent and time independent conditions as well. So now we are going to talk about the two-dimension heat equation that is basically called Laplace equation in the steady state. So it is in the steady state, right? Which means that dou u over dou t is equals to 0, right? So here we can see that on the right hand side it's 0, which means that this is dou u over dou t is equals to 0. So this is called Laplace equation, that is two-dimension heat equation, right, in a steady state. So here we have a metallic plate. This is a metallic plate, and we are going to find the behavior of temperature in the metallic plate uh, in the rectangular Cartesian coordinate system. So the boundary conditions are given: ux comma 0, ua comma y, ux comma b, and u0 comma y, right? So for this these boundary conditions, we are going to solve this particular Laplace equation to find the general solution. So it's also called the Drichlet problem for rectangle when normal boundary conditions are given, right? So ux comma 0 is 0, ux comma b is 0, u0 comma y is 0, and ua comma y is equals to function of y, right? So here this point is 0, this point is a, this point is b, and this point will be a comma b, right? So now we can solve the equation by using the method of separation of variables. We already know how to construct the formulation. So here is the phenomena of separation of variable. The temperature u is function of xy, that is equals to x times y. We will find the derivatives of u xx, uyy, partial derivatives of x and y, and then we'll construct the equation accordingly, and then we come up with the y double prime over y is equals to negative x double prime over x is equals to lambda, right? We can also write this equation in this way: x double prime over x is equals to negative y double prime over y is equals to lambda, right? So we can write in both ways. Now we will solve for case 1 when lambda is 0. So x double prime is 0, y double prime is 0. We already know that the solution for x double prime is equals to 0. This is a second order homogeneous ODE. And again, this is again ODE, second order homogeneous. So this is the solution for the equation. Now we'll apply the boundary conditions. And so we have the boundary conditions for y at 0 and y at b is equals to 0. So these are the suitable conditions to apply here in this equation. And we will get C3 is equals to C4 is equals to 0, which means that u of x comma y is equals to xy. That will be 0 if we plug 0 in place of this y, right? Because C3 and C4 are 0. Therefore, the solution is trivial. Now we will check for case 2 again. We have the equations. Now we are using the boundary conditions for y because we are given with y 0 is equals to 0 and y of b is equals to 0, right? So it's suitable to solve for y. Here we can see that this is y of 0 here, this one, right, and y of b, both are 0, so we can use these conditions effectively, right? So now this is the solution for x and this is the solution for y. We will apply the boundary conditions for y, and then we will get C7 and C8 0 because we will have two differential equations, two equations, that is C7 plus C8 is equals to 0. for y of 0, and then we will have for y of b c7 e to the power pb plus c8 e to the power e to the power negative pb, right, equals to 0. When we will solve these equations, we will get c7 and c8 0. So again, we have a trivial solution. Now we will check for case 3 when lambda is less than 0, and therefore lambda is equals to negative p square. So here we go. Here we can see that negative x double prime over x is equals to negative p square, and y double prime over y is equals to negative p square. We'll construct the solution by solving the ODEs. All right, both are the second order non-homogeneous ODEs. So here are the solutions. Now you'll apply the boundary conditions, right? So these are the boundary conditions for this equation. From here, we can get a is equals to 0 by applying the condition y of 0 is equals to 0, because this will be a cosine 0 plus b sine 0 is equals to 0, which implies that a is equals to 0, right? And then we will apply y of b is equals to 0. Therefore, b sine pb is equals to 0, which means pb is equals to sine inverse 0. And then sine inverse 0 is equals to n pi. We already know from the previous lessons, right? So p is equals to n pi over b. Then the solution y of y is equals to b sine n pi b, right? Now we'll use the conditions for the equation of x. So we have first condition for x is x of 0 is equals to 0. Therefore, we will have c9 plus c10 is equals to 0, which means c9 is equals to negative c10. Therefore, we can write x of x is equals to c9 e to the power n pi x over b minus c9 e to the power negative n pi x over b, right? So it will be 2c9 times this function, where this is equals to sine hyperbolic n pi x over b. All right, we multiply and divide by 2 to make this function the hyperbolic function, right? So it's easier to formulate this function. So now x of x is equals to 2 times this function c9 sine hyperbolic n pi x over b. So now our ux comma y is equals to this function, right? Now we can write bn for 2c9 and b, because this is a constant, so we can write it in this way, bn. So the general solution will be uxy is equals to summation n is equals to 1 to infinity bn sine n pi y over b times sine hyperbolic n x n pi x over b. Now we'll apply this condition, that is u of a comma y is equals to function of y, right? So we will plug a in place of x. So we will have this function sine hyperbolic n pi a over b, where this will be a constant now. So we can use the Fourier series to solve the problem. So sigma bn sine n pi y over b is equals to f of y over sine hyperbolic n pi a over b. And now we can find b by using the Fourier series from 0 to b, right? So this is a function of y, and y is from 0 to b. All right. So this is the idea, and we will find bn and plug in the original equation, then we will get the particular solution. Similarly, if we are given with these boundary conditions, now here we have a function of x at ux comma b. In the previous example, we have u of a comma y as function of y, but now we have a u of x comma b as a function of x, right? So similarly, we will solve the problem by using the separation of variable in this manner. And now we will solve for 3 cases: lambda 0, lambda greater than 0, and lambda less than 0. So we already know that for case 1 and case 2 we have trivial solution, so we just need to work for case 3. So here the solution will be in this form, where we will apply case 3. All right. So now this is an sine n pi x over a times e to the power n pi y over a minus negative n pi y over a. So again, we can multiply this by 2 and divide by 2 to make it a hyperbolic function, right? So this is equals to sine n pi y over sine hyperbolic n pi y over a. Therefore, we multiply and divide by 2 here. So we multiply it by 2, and this will be now sine hyperbolic n pi y over a. Now for 2an, we can plug cn, right? So it will be summation cn sine n pi x over a times sine hyperbolic n pi y over a. Now we'll use this condition ux comma b is equals to f of x to find this cn, all right, by using the Fourier series. So u of x comma b, we will plug b for y. So here y is equals to b. That's why here it's n pi b over a. Now this is a constant. This whole function becomes constant, and now you can find cn by using the Fourier series here, right? So in this way, we can find the solution for the problem. And here we can just integrate f of x with sine n pi x over a to find the particular solution for the problem. Now we will take an example. So here is the example uxx plus uyy is equals to 0. And given the boundary conditions, so we already found the general solution for these boundary conditions. So we'll write it directly here. We know that the solution for this type of problem is given by this equation. All right, so we just need to find the Fourier series. We need to find this particular value, right? So we know f of x, that is equals to sine n pi x over a. So we just need to find the integral from 0 to a, because we know that x is from 0 to a. Therefore, we are going to formulate this integral sine n pi x over a times sine n pi x over a, which is sine squared n pi x over a from 0 to a, which is equals to 1 minus cosine to n pi x over a, because we are using the angle identity, that is sine squared theta is equals to 1 minus cosine to theta divided by 2, right? So 1 minus cosine to n pi x over a divided by 2, that is 1 over 2 minus cosine to n pi x over a divided by 2. Then the integral of 1 over 2 is 1 over 2x minus the integral of cosine is sine. So we will apply the limits that are from 0 to a. So it will be half times a minus 0, because this whole function will be 0, and I will apply a here. So a in place of x here, so it will be 2n pi. So sine 2n pi is equals to 0. And again, sine 0 is also 0. Therefore, we will only get 1 upon 2a. So the value of the integral is 1 upon 2a. We will plug in the equation in the general solution. So we just applied the value of the integral, that is half times a. So 2 and 2 cancels each other, this 2 and this 2 and this a and this a. So finally, we get the particular solution for the given problem, right? So in this manner, we can solve the Laplace equation for the Drichlet problem given the Drichlet boundary conditions. All right. And in the next lesson, we will talk about the Newman boundary conditions, and then we'll move on to the mixed boundary conditions, right? So that's all for the time being. Thanks for watching the lesson. Goodbye.